Hello, everyone. Welcome to this presentation on how much memory do your objects really use. Let me know if this sound is okay. If you have any issues, please do tell me, or please do tell me if you can hear me. Great, thank you. So there should be there's a link in the chat for if you want directly on the website that I'm presenting. It might be a bit easier because it'll use less bandwidth than the streaming, and you might get better quality also directly. So there will be a bit of code, so I recommend you do that actually. So I'm Martin Devillers. I'm an Android developer at Dashlane, and I'm going to be presenting, well, some general concepts on how memory works on the JVM. And the objective is for you to be able to understand better the memory implications of any design decisions that you might be making within your app, so that you can make them being well informed, and so that if memory is going to be an issue, you can understand why and how to correct it. So the big objective is this, the out of memory error. So depending on the app that you're working on in everyday life, this might or might not be something which is a big concern. But in general, when you work on Android, you're working on phones. So at some point you run into that situation where the phone doesn't have enough memory to allocate to your app, and then you get a crash. That's what the out of memory error is. It's when the JVM can't allocate an object, because basically the heap that your object needs to be allocated on doesn't have enough size anymore. And even when freeing up objects, it can't find any. And it's a tricky error, because when you get that error, the stack trace that you're going to be getting isn't necessarily going to tell you why you got the error. You get the error is thrown because there isn't any memory to allocate, but it doesn't tell you where the memory is being used at that particular moment. So in order to avoid these errors, you have to really think about it early in your design considerations. And you have to understand what you might be doing, which is causing all the memory to be used up. So let's look at why you get this error in the first place. What are the common causes? Well, if you look around the various documentation, you'll find that a very common cause is memory leaks. So memory leaks happen when you're creating objects and then you're not removing references to them, even though you're not using them. And these objects can accumulate progressively, and you get more and more of them. And ultimately, since you're not freeing any memory, if the curve just keeps on going up, then at some point you run out of memory. So what do you do against this? Well, you code properly so that you don't have any bugs, you don't have any memory leaks. You make sure that you don't keep any references to activities and views outside of their life cycle, because these are actually pretty big objects that themselves have a lot of references to objects. So you make sure you free up these references correctly. A second very common cause is bitmap allocation, because when you load an image to display it on screen, you have to turn it into a bitmap, which is basically just a pixel by pixel representation of the image itself. So if the image has a high resolution, this can lead to very large arrays of pixels. So the way to avoid these issues is, well, honestly, just use a library. There's some really good ones out there which will take care of allocating the memory, managing it, and scaling the image as needed for display. So there's some good tools out there, and this is a well-documented problem. The third one is when you're doing I/O and data processing. So if you load a file, you can easily load something which is very big and which uses up a lot of memories. So if you load a big text file with a bunch of lines into a string, you can get an out-of-memory error. So keep that in mind. And if, for example, you're just looking for one line within a text file, then Kotlin provides you with some great tools to have like a sequence of lines and just keep the one that you're interested in, rather than loading the entire text and then filtering out. And the last cause of memory issues is when you're just manipulating large data. So you have a huge tree of nodes, you have a lot of objects allocating because you need to keep track of what's going on for various reasons, but you just have a lot of data, a lot of objects that you're loading, that you're manipulating. And this is one that we're going to be using, that we're going to be interested in right now. This is an issue that I found myself investigating when we were considering some evolutions to the way we handle the user data within our Dashlane app. And the question, to put it simply, was, How about if we just loaded all the user data into memory and just kept it there for the whole life cycle of the app? How much memory would that actually be using up? And would it be an issue for large accounts? Would it just use up all the phone's memory? So this is what I'll be going over. And the idea with this presentation is to look at the theory and the specification of the JVM, because it's something that we don't necessarily go over in depth during our training. So I'll go over how it works, how it allocates the objects and uses up its memory. And then I'll look at the instrumentation tools. You'll see why the theory actually has its limitations in practice when you're trying to really understand the memory. So I'll show you how the instrumentation tools work so that you can examine it at runtime how much memory your objects are using. And that way you'll be able to see exactly how it works. So first, going back to the basics. What are all the data types in Java? So you have all the numeric types that are shown here. The size of these in memory is pretty fixed. You can't really do anything about it. An integer is always going to use 4 bytes, so that's 32 bits, because that's the specification. It's a 32-bit integer, that's how precise it is. So these are always fixed. Then you have the Boolean type. So the Boolean type uses always 1 byte of memory. But you could argue that it doesn't really need 1 full byte to represent true or false. And that is true. And there are some JVMs that allow some settings so that you can configure this type of optimization to have a more compact use of memory. So that, for example, if you had an array of 8 booleans, you could represent them each on 1 bit of a byte and then use up less memory. There's actually a data structure in the standard libraries which does this for you, which is called a bit set. If you're not familiar with it, it's generally not useful because this optimization is generally not needed. But anyways, I just put a little asterisk there because the Boolean can take up less than 1 byte in certain configurations. Then you have the character. So since all the JVMs use UTF-16, they always use 2 bytes for this. You have a reference. So that's basically like a pointer to an object. So references will use 4 bytes on a JVM, on a typical one. If you're actually using a 64-bit heap for the JVM, so I talk about the heap because it's actually not really the OS itself which matters. You can be on a 64-bit OS, but using a 32-bit JVM because you don't need to have such a huge heap for all the objects. But anyways, if you're using a 64-bit memory, then you need 8 bytes to keep an address. So keep that in mind also if you want to use a 64-bit addressing for your JVM, then you're going to double the size that all the references use. And then the last 2 types are the arrays and objects. So they're basically the same. So I'll start with the object. The object has a 12-byte header, which contains information on the type, etc. And then has the size of all the fields that it contains. And that is always padded on all JVMs. They pad that to the nearest multiple of 8 bytes. The array works basically the same, but it has to keep track of the size of its contents in addition to that. So that's why you see there's a 16-byte header, which is just because it includes this. It includes this size property. So these two structures are always padded to the next multiple of 8 bits. We'll see exactly in some examples what that looks like. So the way we're going to look at the objects at runtime is we're going to use something called the instrumentation tools in Java. So for this, you have a class, it's an interface actually. You have an instrumentation interface which provides a getObjectSize method. And the documentation that I copied here tells you this returns you what they call an approximation because they can't provide any exact guarantees. But basically, it gives you the size of the object in bytes. So how do you use this tool, this instrumentation package? I created a project for this in Gradle. So there are two different sub-projects in Gradle. There's the one which is the one that we're actually going to be examining for the memory usage, and then the agent, which contains all the instrumentation tools. So within the agent project, I have an instrumentation agent class, and within the instrumentation project, the one called instrumentation, I have just a main class, which is going to be run like an application. This is what the instrumentation agent class looks like. So the pre-main method is a convention. It has to have this exact signature, and it's called at the beginning when you launch your app, and it passes the instrumentation instance. So we keep a reference to that. This way, later on, we can use it to get the size of the objects. And so we encapsulate that and we just expose the getSize method, which is going to be called by our main app to investigate its own objects. You have to register in the manifest for this package what the pre-main class is. So this is something, this is all part of the documentation for instrumentation on Java. It's all just a completely standard. And in the project that we want to instrument, we tell it that in the command line args, we give it the Java agent, which is the jar of the other projects. And we also put that it's a compilable dependency so that we can reference its classes. So using this, we can basically just call the getSize method with any instance from our projects and see how much memory it's actually using. So that way we can see how our specifications that I showed earlier translate in practice. So if we have an empty byte array, so like I said, arrays always have a 16-bit header and then 16-byte header, sorry, and then they have the size of their contents. So an empty byte array just has a header, so it's 16 bytes long. But if I add 1 byte, it has to round it, add some padding so that it's the next multiple of 8 bytes. So it uses 24. And then if I add a second one, a third, and up to 8 bytes, then we're still on the same size because we already had the padding, so we're just using that already. And then if we add a 9th one, we have to pad to the next multiple of 8, so we use memory. So you can see with this why you'll often find buffers that use a multiple of 8. In reality, they actually often use a power of 2 for their size when you're doing byte arrays. It makes sense to just not waste memory that would be used by the object anyways, but that would not be usable within the program. So looking at another simple example, if we just create an object, so an object that doesn't have any properties, like I said, it has a 12-byte header, and that's it. But it has to pad to the next multiple of 8, so that's 16 bytes total for this object. I can add up to 4 properties, byte properties, that is. It'll just use up the padding, so it doesn't take any more space. And then if I add 1 more byte property, then it has to pad to the next multiple of 8, so we use 24 bytes. So on. If we're only storing bytes in objects, and technically for memory, you want to have like a 4 plus a multiple of 8, not that it necessarily matters in terms of memory usage. But this is all nice, but we're examining some really simple structures right now. We're just like objects and arrays of primitive types. So now what we're going to build is a program which inspects a whole graph of objects, so that when you create a data structure, you can see how this whole structure and everything is references how that uses up memories. And we're going to use a combination of the instrumentation and the reflection APIs to do this. So our goal is to build this method, the get object graph size on any instance. So we're going to recursively go through all the references. So we have to keep track of everything we've already visited so that we don't run around in circles and end up with a Stack Overflow. So we have this set to keep track of everything we've already visited. And if we haven't visited the object, then we get the size of the object itself. Then we find any references it might have to other objects, and we add all those too. So how do we get the size of everything it references? Well, if it's an array, then we're going to get all the references from the array. And if it's an object, we get all the references from the object. In order to get the references from an array, we first check whether it's not a primitive type, because primitive type arrays don't have any references. And if it is not a primitive type, then we get basically all the values from the array, and we recurse on the original call to get the size of all these values. And for an object, we use the reflection, Java reflection, to get all the fields that are not of a primitive type and that are not static. We get all these references. And again, we recurse to get the size of all these. So once we do that, we have the complete size of an object and everything it references and everything these instances reference and so on. So let's look at a simple example. We have our hello world string. and we examine the size of this. So it tells us this is 72 bytes in total. Where is this coming from? If we look back at our specification and if we look at how this string class works, well, the string class has two properties, a char array and an int. So that ends up being 24 bytes just for the object itself. And then the char array itself needs 48 bytes. There's 13 characters, and rounding up to the next multiple of 8, plus the header for the array, you get this result. Now let's look at a different structure. So we have this object which has 4 fields that are all strings, and we end up with 256 bytes for the total size. So this is what I'm going to be interested in. What's the difference between using this structure to keep all these values? So the keys here are just randomly generated strings that I generated. And what if we were to just, rather than use an object, we used a map, because we wanted to be able to mutate this and to put whatever we want into it. So what are the size implications? So like I showed here, we just have these 4 reference fields within the object, and then you have the string values. So the total size is 256 bytes. So I create a linked hash map, and I fill it with the same values, and I end up with 744 bytes. So the overhead is caused by the map structure itself, all the entries which need to be allocated, and the strings that are in the keys. So you can see that's quite a bit of overhead just for using unstructured data rather than putting it into an object. And just to FYI, also the reason I'm using a linked hash map rather than using mutable map of is because I'm going to perform some comparisons. And when you call the mutable map of method, you can see if you look at the source code for Kotlin, it performs a bit of optimization on the size of the map that it's creating. So it'll be a bit smaller. It doesn't really make a big difference, but it's just like to be fair to the other data structures that I will be using, which don't have really this optimization at creation. I wanted to use the linked hash map like this. So to look at the overhead, exactly where that's coming from, let's look at all the references. So I included in the code that browses the graph, I included something which creates the actual image of all the references that we've browsed. So you can see the linked hash map, all the overhead that it has. There's the object itself. There's the array from the hash map. You have all the entries that are linked hash map nodes. And then you have the keys themselves that it has to allocate in addition. And with all this, we end up being with this data structure, which is almost 3 times as big as the original object which we had. So you can see the advantage using this structure. By looking at this, you can see the advantage of using an object and doing a proper parsing, for example, of your JSON objects, rather than keeping the original JSON structure. If you parse all the values and put them in the object, you're saving a lot of memory, actually. So we can compare, because linked hash map is just about the most greedy map structure you can have. It has to keep all the references. So can we look for something a bit more optimal? Well, for starters, let's see if when we remove all the linked list references that the linked hash map uses to keep the order, we use a simple hash map. Well, we get a bit less overhead. We can also try a tree map, which is a bit more of a more simple structure. So that also removes some overhead. Then we can look at the collections from the Android X library, which is, again, another different structure. I'm not going into all the details, but which aims to reduce the amount of memory used. So the array map uses significantly less overhead this time. Now we're down to only about twice as much memory as an object. And most of that now is due to just the fact that we have to allocate all the keys in the map itself, rather than just having fields. And then we have an even slightly more optimal data structure, which is called the simple array map, which is used also in the Android X library, which is a bit smaller again. So it's interesting. We can already see what is the memory impact of these supposedly optimal data structures. And it does, I mean, you do compare, when you go from a linked hash map to a simple array map, you do lose like about a quarter of the memory usage. There is an impact, but it's not going to dramatically change everything. So hopefully this all gives you an idea of the impact of using these types of maps. There's a lot of factors that will change these results. So in this case, I had 4 entries And I think the size that I used for the keys was 6 characters. So 4 entries with keys and values that are 6 characters each. So if you play around with these parameters, you'll get some very different results. If you add more entries, if you have a different load factor. So the load factor, if you're not familiar enough with it, when you have a map, it works like basically like an array list. It needs to regularly grow to be big enough for all of its contents. So if you have a high load factor, then you'll be using less memory, basically, because you won't have as many free slots in the array. So that's going to impact the results that I just showed. The size of your keys, because obviously if you have bigger keys, then using an object is even more important because you don't have to allocate the strings for these keys. And the value also, if you have big values, then basically the overhead is going to be negligible. So this table is just like, it goes to show you how this whole tool that I built works to give you the size of the objects and how it can give you information on the size they use. But the results shouldn't be used as is. In short, what I'll say is know your use case, know whether you're going to be manipulating large keys, large values, know in general also whether memory is going to be an issue or not for you. So we'll look at our case study that I mentioned originally. So we wanted to build our in-memory database to keep all the user data. The data structure that we're using is basically when we have an item. So an item is something that the user has stored. It's essentially like a JSON. So you have the data, which is a steel class, which can be a string, a list, or a map. So you can argue, of course, that having this steel class for type safety adds additional overhead, and you're completely right. So when I did this whole study to check the memory impact, I looked at whether we could have something more optimal by not having the steel class wrapper. It did have an impact, of course, but it was still not sufficient. I'll going to go over that again. But yeah, this is the data structure we're going to be using, a recursive tree of objects. And I pulled some sample objects from that users were using or that we had in some of our test accounts. And this is how big the objects are. So the settings object is something that, which is basically all the settings for the user. The address, I'm not going to explain to you how the entire product works, but we have to store these types of things like address and passwords. And some user accounts have a lot of them. So to give you an idea, if we have 10,000 items and an average size of 3 kilobytes, which seems like a good estimation given the benchmark I did, then you end up with about 30 megabytes just for your in-memory database. So then you ask yourself the question, is that a lot? Is that something which is acceptable? Honestly, that's not necessarily an easy question to answer. It really depends on the phone. If you take, for example, a Pixel 3, which is a relatively recent phone, more on the high-end spectrum, it tells you that it has a heap size of 500 megabytes. So it's for that kind of phone, it's not negligible, but it seems manageable. But then again, like I said, that is a fairly recent and fairly high-end phone. So if you want to support a wide range of users, this seems unacceptable. It seems like something which is going to be leading to a lot of errors. So that's why we decided to go for a different solution, which doesn't involve loading all the user data right at the beginning. So if you want to take a look at these tools, I have the GitHub link right after. You can use them to inspect your own data structures. It can give you pretty quickly an overview of how much memory you'll be using up, rather than having to do pen and paper work to calculate, oh, I have this field, I have this field. If I have like 5 objects referencing each other, how big is that going to be? You can just use this instrumentation API to check at runtime. It works pretty well for that, and gives you an overview, of all the memory you'd be using with a given data structure. So you can make informed decision. You can just copy paste into the project like your own data structure, see what it looks like. So this way you can look at for example, the object overhead if you're using like wrapper classes, like what I just showed with the steel class, which adds some type safety. you can see how much impact that actually has on your data structure. You can also see, for example, if the primitive type wrappers will have a big impact. You know that when you're using a map, for example, from an integer to an integer, then all the int values need to be wrapped in the integer class, which can be costly. So then you have the classes from Android X which optimize that, like the sparse array. So you can use this project to test exactly what is the impact of that with all the boxing of the primitive types. You can check, so I put the raw collections, so you can check exactly what's the impact of keeping a raw collection of objects. So that's the example that I just showed earlier of using a map to keep all the values, creating an object and parsing the JSON so that the values are put into an object. So obviously putting them into an object is going to use less memory, but there might be also some business reasons that you don't want to do that because you need to maintain the entire original structure. And you can also see the impact of manipulating large strings and that sort of thing. So don't be afraid to look at it. It's not too complicated, but at least try to understand how everything works, how these design decisions are going to impact the overall memory usage of your app. And here are all the links. So we have the GitHub project. We have all the code that I just showed. The slides right here. And if you want to follow me on Twitter or on Medium, I'm not extremely active, but I do occasionally post some stuff. So you can go ahead and do that. And so thank you for your attention. I'll be going to questions now. Are local arrays allocated on the stack, or are they just a reference on the stack? If yes, do they have the same overhead, including padding? So I didn't talk really a lot about stack versus heap, but basically what I was interested in is the size that all these objects are using on the heap itself. For the stack, to my knowledge, for example, if you create an array within your code, so the array itself is going to be allocated within the heap, and within the stack, you'll just have like your reference to that address within the heap. So it'll just use up the size of one reference. That being said, all this that I'm talking about is always hard to really predict in the JVM runtime because you never know what kind of optimizations the JVM is doing. So there could be some fishy stuff going on JVMs, which means that what I'm saying is not true. But in general, my understanding is that, yeah, if you allocate an array, then you get the size of the reference, which is added to the stack, and then the array itself is allocated within the heap. Are there any other questions? Yes, it is. All right, so another question is, based on my experience, what has been the most efficient change you did in your code to reduce the app size? There's a lot of things. Honestly, one of the things that was extremely impactful that I did was to make sure that when we were processing data, we were always using buffers and IO streams. We have basically some, everything in our app is encrypted. So when we manipulate user data, we have to base64 decode it, then pass that into a cipher to decode it. Then we have to pass that into a parser, et cetera, et cetera. So if you're making sure that you're not loading each intermediate step completely, so making sure that you're not taking the data from the base64, turning it into a big byte array, then turning that into a big byte array, which is decrypted, then into a string, then that helps you a lot, basically. That'll be much, much more memory efficient if you make sure that, every time you're using buffers and you're just doing it by chunks. Let's see. In which extent do you think that going that into data structure details is efficient for your app? For example, a minimum data size. Basically, this tool is useful to estimate what is impactful. For me, it was about, well, for us in general on our team, it was about checking whether certain solutions were viable or not, like whether we could use certain data structures and they would just lead to an absurd amount of memory being used. And it's also useful just to see whether by changing certain elements in our data structure, we can really improve on this. So we can see if, like I said, for example, if we get rid of the type safety and safety of C classes, is that going to be impactful, or is that just useless marginal optimization, which is not going to change anything? So I think going into this level of depth is not necessarily, it's not necessary in every situation, but when you are considering some architecture decisions where you're like, is this really going to be a problem in terms of memories? This can really give you the information in big detail. Yeah, I'm being told I'm supposed to change to. Do you want to look at the questions? Yeah, so like I was saying, let me just change some of those around. Sorry. Like I was saying, yeah, it helps you get something that you're get the information that you're sure of, and it helps guide your decisions. The next one, based on your experience with, though I answered that one. What is the most efficient change you did in the code reduce app size? Do I monitor famous bitmap libs like Light or Picasso? No, sorry, I have nothing. I didn't check whether there's any differences in what they do. I assume it's pretty much the same thing in both cases. You want to make sure that you're cleaning up the memory after using it, so you recycle the arrays when it's relevant. And if you're displaying something within a view which is pretty small, then you sample the original image to make sure that you're not loading it too big. All that is pretty classic, so I would assume they do more or less the same. I think the main differences is with the tooling they use, like using coroutines or using different tools for threading and different APIs, but I imagine they do sort of the same thing. Our channels flows are prone to memory leaks. That's kind of a different topic, but sort of. I mean, in the sense that to me, that's more of a cancellation question. You have to make sure that you're, since cancellation is always cooperative within coroutines, if you're not handling the core cancellation correctly, then you're going to keep tasks running and keep references to objects for a very long time. If you do handle cancellation correctly, then as soon as your task is stopped, all the references will be released. So yeah, to me, if you're afraid of memory leaks, want to look at whether you're handling cancellation correctly within coroutines. And the last question I also answered. Is there any difference advice compared to standard Java when using Kotlin? I mean, basically you have to know how Kotlin translates to Java. And there's a lot of topics that have been done on that kind of a Kotlin under the hood. So yeah, there's a lot of things about that, about how the classes are created when you compile Kotlin code. But then once you know how it's compiled, then it works the same. But in general, Kotlin doesn't add that much memory overhead now. Not on the stack, at least. Sorry, not on the heap. On the stack, it does create a lot of variables, but I think that's probably insignificant anyways. Is memory usage always the same in Hotspot, Delvec, and Arts? No, that's why I mentioned different JVMs might have different configurations. I think if you remember, I was talking about how you can configure Booleans to be optimized to be packed together. I'm pretty sure I read that about the Hotspot JVM, that it has this feature, which has to be enabled. It's not enabled by default. So that's an example, but I believe there's some subtle differences. But the overall behavior is generally more or less the same. All right, that's all. Thanks to everyone for attending. I hope you learned something. and I hope it was clear enough. Enjoy the rest of the Android Makers Conference. Thanks to all the organizers again. And yeah, have a good couple of days.